Hello, students. We are going to see the fourth module where you will be in the last class we have seen about the dynamic programming. So now we are going to move on to the greedy technique. So when you say it as greedy technique, we have different algorithms like a Prim's algorithm, Kruskal algorithm, Digit. So in greedy technique, we are going to see Prim's algorithm, Kruskal algorithm, Dijkstra's algorithm, and the Huffman trees. So here, when you say it as the greedy technique, we have to see what is the concept behind it. So here, when you say it as a greedy technique, it is going to construct a solution to a optimization problem where you will be going stage by stage. So when you go ahead with the steps, every problem, when you say it as an optimization problem, the problem will be having certain constraints. So you need to satisfy the constraints. So you have to see whether the partial solution which you have obtained is feasible or not. Now, each stage, since we say that it is an optimization problem, it can be a maximum value or a minimum value. So when you say it as the optimal solution, for each stages, it has to be optimal. So we say that it should be a locally optimal, not the for the entire solution, the partial solution. That is when you choose a particular stage or step, whether it is a feasible solution and as well as an optimal solution. Third thing which you need to remember is when you go for the greedy technique, here we are saying that it is not irrevocable. That is, once if you go ahead with a step, when you step forward, you will not be able to get the output. So here, if at all you want to do any changes, then you have to restart doing it from the beginning. So that's all about the greedy technique. So greedy technique, it's an constructing a solution to an optimization problem, and it will be going by step process. So when you make step by step process, it will be having a step going through a sequence of choices. The choices you are going to make, we have to check whether it is going to be a feasible one, whether it will be a locally optimal, that is for each step, whether it is giving you an optimal solution. And once the choice is made, it cannot be reverted. So if at all, if it has to be changed, it has to be, you have to redo the problem from the beginning. So for some problems, it gives you a optimal solution for every instance, but for most of them it will not be does not, but can be useful for the cost approximations. So we have seen in the first introduction itself, there is something which is called as the exact and the approximation. So based on what type of problem you have taken, what type of solution you require, based on that we will be using the two techniques. So in the dynamic programming, if you see, the dynamic programming, we are having the overlapping subproblems, and these subproblems will be solved once. Like a Fibonacci series, where Fibonacci series, when you talk about Fibonacci series, we have seen that for finding the Fibonacci of 5, it will be depending upon the previous two consecutive integers, that is 4 and 3. For 4, again the same 3 will be repeated. So we say that it is overlapping subproblems, whereas in greedy, the name greedy itself suggests that you are going to be greedy about some solution where you will be aiming for an optimal one. So here we are going to construct a solution to an optimization problem step by step, where you will be having a set of choices. The choices made should be either feasible, or it should be locally optimal, or it is irrevocable. That you have to keep it in mind. So when you go for this, we are going to see whether it can be done for an optimal solution for every instance, whether you will be getting it, or you will be seeing that whether you will be getting a fast approximation growth. Clear? So this is a greedy strategy, where we can see that in the greedy strategy there are various applications. Okay, first of all, I have told you that it can be either an optimal solution or it can go for an approximate one. So when you say it as an optimal solution, for example, if you have the change making for the normal coin denominations, we will be saying that it is an optimal solution. Minimum cost spanning tree, you create a spanning tree where it gives you a minimum value. Next, you will be having a single source shortest path problem, simple scheduling problems, Huffman codes, all these comes under the greedy strategy. Okay, whereas the approximation, you have seen the traveling salesperson problem, you have seen the knapsack problem, various combinatorial problems. We have used the Johnson Trotter lexicographic minimal change algorithm, everything for to create various subsets. So all this comes under the approximation algorithms. So now we will talk about the change making problem. Change making problem is nothing but it is going to have a decision. What's the decision all about? You will be given with unlimited amount of coins. Okay, for all the denominations, you need to get a change for the um, coins, where you are saying that you will be using various denominations, and you see that if you want to get minimum number of coins, we will be going according to that. So for example, suppose if you are given with the coin as 48, so here you will be having various denominations. You take all those denomination and prepare a change for the 48 cents. So the greedy solution is where you will be going for an optimal for any amount and normal set of denominations, and it may not be optimal for the arbitrary coin denominations. So here we go with the spanning tree. What do you mean by a spanning tree? A spanning tree of a connected graph is nothing but it is a acyclic subgraph. Okay, so when you take this graph, it will be including all the vertices. So it should not be a cyclic graph. Here the graph given is a cyclic, so you should see to that it is not a cycle graph. So the minimum spanning tree is nothing but among the spanning trees, whichever gives you a minimum cost, that is considered as the minimum spanning tree. Now what is weight of the tree? Weight of the tree is nothing but the sum of all the weights of the edges. So here, if you see this graph, okay, we are saying that we are going for the graph where you will be using it for various purposes. So when you go for this, if you see, you can see to that you will be using a you will be using a graph structure where you will be just saying that we need to um, go for the um, spanning tree. So here we will be just taking a spanning tree which will be giving you a least cost. For example, supposing you take that you want to go for the spanning tree. So here in this spanning tree, you are given with the value of a. So if I say it as a, you will be seeing that this spanning tree is a to it will be going for b, then from b it will be moving to c, then it will be, for example, this is your A, B, you can create a graph as C, then you will be saying that it is going to D. This is one spanning tree. Okay. Similarly, you can have another, create another spanning tree which says that this is A, this is B, and from B it will be connected to C, and also it will be connected to D. This is another spanning tree. And one more you can have, for example, not one more, you can have different spanning trees, just taking it as an example. A to C, you can also have it as A to D, and you can also have as A to B. This is also a spanning tree. See, in each one you might have noticed that you have this is a spanning tree where it is consisting of all the vertices, but it is a subgraph and it doesn't have a cycle. Here also it is covering all the vertices, but it doesn't construct a cycle. Here also, if you see, it is having all the vertices, but it is not a cycle. So from here, you can see that whenever you go for the values, if at all you are given with uh, now if you are given with this spanning tree, so the spanning tree whatever we have taken is, see here you have it as A to C, you have it as all these can be considered as different spanning trees where you will be choosing the edge. For example, if you see this spanning tree A to C, what is the edge cost? 6. A to D, what is the cost? D. So like this, if you find out the various ways, you will be getting to know what is the mm, uh, what is the thing for each and every one. So based on this, you will be seeing that there is um, you can you can construct the spanning tree and find out which is the least cost. Okay, so this is how you will be creating a spanning tree. So now we will go for the minimum cost spanning tree. Now, when you say it as the minimum cost spanning tree, um, we cannot just draw various tree structure and find out which is minimum. So what we are doing is we here as the number of vertices grows on, the number of spanning tree to be grown will also be exponentially larger. Second, generating all the spanning trees, it's not a feasible one. It will be taking a lot of time. So what we do is we have two algorithms. One is the Prim's algorithm and another one is your Kruskal algorithm. In the Prim's algorithm, what we do, you will be starting with the vertex. Okay, you will be growing the tree one by one at a time by expanding the subtrees. So on each iteration, when you are adding the vertices, you can say that it is almost a complete tree structure. It it should not be a disjoint one always. It should be connected, but it should not have any cycles. So when you consider all the vertices, you can stop the process. So here you are given with a graph. What we need to start it, we will be starting it arbitrarily. So we will see what are the steps to be followed. So here in the algorithm, it will be making vertex where you will be seeing there are two sets. One is the fringe and another one is the unseen. So whatever the fringe will be containing only the vertices that are not in the tree, but at least adjacent to one of the tree vertices. So that can be selected. In the unseen vertices, all the other vertices will be there. They are yet to be seen. So if at all there is a tie, the tie can be broken arbitrarily. So once if you identify a vertex, you have to add it to the tree where you will be performing two operations. Okay, so for each remaining vertices, we will be seeing how the performance will be going on. So for that, we are given with an algorithm also. So what is the algorithm? BT is nothing but a, empty set, vertices V0, and the edge will be empty. Okay, so for n minus 1 times, if there are n vertices, we know that always in a graph, if you have n vertices, you will be having n minus 1 see, this is a graph. In this graph, there are 4 vertices. So when you create a spanning tree, the spanning tree will be consisting only of 3 vertices. Okay, sorry, 3 edges. Okay, always if there are n vertices, there will be n minus 1 edges will be there in the spanning tree, which we have already drawn the tree structure. So among those tree structure, we are going to take the minimum one. So here when you say it as the Prim's algorithm, we have an algorithm which is following this. So it will be performing n minus 1 time. So you need to find out a minimum weightage where among the subsets, and you will be joining it. We have the operations called as union operation, which will be used for the Prim's algorithm. Now, when you say it as the Prim's algorithm, we are going to take one small example. Okay, so we will see how to work out with that small example. Okay, so here you are given with the condition that when you say it as the subgraph, you have to consider all the vertices. All vertices should be connected and there should not be any cycles. And what is the minimum value? The sum of all the weights edges should be considered as a minimum one. So if you are given with a graph, now when you take a graph, for example, if you say that there is a graph which is existing like this, take a graph. Now what we have to do is we need to choose an arbitrary vertex. So usually when you say it as choosing an arbitrary vertex, we will be starting vertex with the alphabetical order, where you will be taking it as A as the starting vertex. Now once if you take the vertex A, then what we need to do in the second step? So here what we will be doing is you will be keeping on including the adjacent vertices. The adjacent vertices also, there will be so many adjacent vertices. You have to consider the nearest adjacent vertex. So when you see the adjacent vertices, what are the edges you have? You have A to D is there, A to B is there, as well as you have A to F also. Among these three, which is the nearest adjacent? The nearest adjacent is, you will be taking it as A to B with the value as 2. Okay, so now we have considered A, B. So A and B are the tree vertices. So here we can see for B which are all adjacent. B to D is there, B to E is there, B to C is there, B to G is there, and also B to F is also there. So now among all these, which is the nearest adjacent vertex? The nearest adjacent vertex among all these is, we are considering it as B to D with a value as 1. Okay, so next you will be including the vertex D, and the edge D to B will be taken, and it is 1. Now so we have included only all the three vertices. Now you can go with the D and find out its nearest adjacent. Nearest adjacent which is unvisited. D to B is nearest, but it is already visited. So you are going for E, and you are saying that E is not visited. Okay, so you will be going with D, which is saying that it is unvisited. And now for E, you have E to C, and you will be seeing what is the next adjacent vertex. Okay, now if you see it as B to E, it is having 3, but can we take it? No, it forms a cycle. If you have a edge like this, it forms a cycle. So you have to, even though it is less, you need to discard, because we are saying that they should not form a, it should not form a cycle. So we are discarding it. So now we have to see, you have B to E with a value 10, which is 3, which is being discarded. Now we will be, why it is discarded? Because it forms a cycle. So now we will be taking B to C and B to F, B to F, B to G also. So which is least, B to G with a value of 4 is least. So we are including that into the graph. Now you have G is in the tree vertices, so you can take a G to F or G to C also. Among G to F and G to C, both are unvisited. Which is nearest? G to F is nearest. So we are considering G to F, whose value is 1. So now, again, is there any, have you done with? No, because how many vertices are there? There are 7 vertices. We have considered only 6 vertices. So now the value is 4, A to D, the value is 4, but it forms a cycle, so we will be discarding it. Now, A to 5 also, if you take, it forms a cycle, so we are just discarding A to F with a value 5. That is also being discarded because otherwise it will form a cycle. Now, when you take G to C, what is the value? It is 6. So, can you take it? Yes, we can take it, whose value is 6. So, now have you understood the concept of the Prim's algorithm? The concept of Prim's algorithm says that you have the tree vertices. Now, among the tree vertices, you are having 7 edges, 7 vertices. We have taken only the we have taken all the 7 vertices, but what is the number of edges? 1, 2, 3, 4, 5, 6. Number of edges is 7 minus 1, it is 6. Now, what is the total cost for the minimum spanning tree? The total cost is 2 plus 1, 3, 3 plus 2, 5, 5 plus 1, 6, 6 plus 4, 10, 10 plus 6, 16. So, the total cost for the minimum cost spanning tree is 16, where there are no cycles. Some of the edges are being discarded. Why it is being discarded? Because if you take those one, it will form a cycle. So we have to consider the Prim's algorithm in such a way that one is in the tree vertices, one is unseen vertices. Only then you can add it. If both are in the tree vertices, if you take the both the edges, for example, if you take A to D, A is also there in the tree vertex, D is also in the tree vertex, and it forms a cycle. So you should see to that it is not forming a cycle. Okay, so this is about the minimum cost spanning tree by using the Prim's algorithm. So this is what in the algorithm we are doing. We have B vertices. So this loop will be repeating B minus 1 time. That is, if at all you have some n vertices, we will be considering it as n minus 1 edges. Now, I hope you would have understood it. Now, how you can depict this? We will be, when you are asked for the exam, we will be giving it as 3 different columns. One is your tree vertices, the other one is the remaining vertices, the third one is the illustration. So first, initially A is kept as null. Why? We have not started with A is an arbitrary vertex, we are choosing it. So now B to A is having a value as 3. Whereas C, it is not near to A, adjacent to A, so it is infinity. D is also not adjacent to A, infinity. E is adjacent to A with a value 6. F is adjacent to a value A with 5. So among these 3, which is the minimum? The minimum is 3. So we are taking it. Now, both are in the tree vertices. So even though A is not adjacent to C, now B is adjacent to C. So you can take B with the value 1. But D is not adjacent, so it's infinity. E is adjacent again with A only with the 6. F is adjacent to, before F was adjacent to A with the value 5. Now F is adjacent to B with the value 4. So among these 3, which is the smallest? The smallest is C, C of B comma 1. So that is also been included in the tree structure. Now, for C, again we are just checking it is near to D. Before it was neither near to A or B. So now it is near to D. So with the value 6, E is adjacent to A with the value 6, F is adjacent to B with the value 4. So among that, again F is near to B with the value 4. That has been taken. Now you have left out with the D and E. Whichever is the minimum value you take. Now E is adjacent to, instead of A, you can take it as F. Why? Because it is having a least value. Before we, from A, we move to B. Now we are moving to E with F with the value as Instead of E of A comma 6, we are now saying it as E is F to F2. So which is minimum? F comma 2 is minimum. So we are taking that, and now we can see that the last vertex which has to be chosen is D of F comma 5. So when you include it, you will be getting a tree structure where it will be consisting of all the vertices. But the number of edges will be always one less than the number of edges will be one less than the number of vertices. So in the fringe algorithm, we have two sets, fringe and the unseen. So based on that, you can, if at all there is a tie also, tie can be broken arbitrarily by using. So if you go for the algorithm, we use a priority queue with a implemented by a min heap. So you will be seeing whenever there is the cycles are not formed, how you can avoid cycles, everything it has to be seen. So if you see the efficiency of the algorithm is based on what is the min heap structure and how you are going to do the various operations. So if a graph is going to be represented as a linked list, and the priority queue is given, which is implemented as a min heap, what is the running time? It will be based on the number of edges and number of vertices. So here we consider the number of vertices. We will be taking it as log v. So the number of edges is e. So the time taken is considered as e into log v. So based on that, we will be seeing in a priority queue, you can do various operations like addition, deletion, updations, everything can be done. So based on that, we will also check for what is the time complexity for all these algorithms. So whenever you see to that, it is a connected graph. In a connected graph, we know that the number of edges will be always greater than or equal to vertices minus 1. But in a minimum cost spanning tree, if you see, the spanning tree will be consisting of a set of edges where the number of edges will be always 1 less than the number of vertices. So based on the data structure which you are choosing it, you can also find out what is the time taken. So any graph given, in the graph we need to apply this algorithm. The algorithm says that you will be always going n minus 1 times, and you will be choosing each vertices one by one. So here, even if you are given with um, a graph which is of very large size, we will be able to do it in a short time, or a efficient algorithm can be done. Why? Because here we are not going to construct all the spanning trees. We are only constructing the tree structure based on the Prim's algorithm. In the Prim's algorithm, we know we will be going only if there are 5 edges, then we, with the 5 stages, we can finish off all the processing where you will be constructing a minimum cost parameter. So actually this is very easy method by using the greedy algorithm. There is one more algorithm in this greedy technique. One more algorithm is there by using the greedy technique, which is your Kruskal algorithm. In the Kruskal algorithm, if you see, you can see that whenever the graph is given, how the graph is being taken, that you can find out easily by using the based on the vertices. So this is all about your greedy technique where you have the Prim's algorithm. So if you are when you have the Kruskal algorithm, please don't confuse between the two. Here we are having the fringe and the unseen. always it will be remaining as a current distance label, where you will be updating the label. And you can also see that in this Prim's algorithm, we can find out the time complexity by saying the proof by induction method, where you will be taking the number of edges and number of vertices. So each edge you will be connecting between two vertices, and you will be seeing what is the time taken. So based on this, we will be seeing the Prim's algorithm. So this is based on the greedy technique, which we have to see. And the next is the Kruskal algorithm, that we will see it in the next class.